Good morning, boys and girls. It's a wonderful Thursday morning. I hope you're having a great morning. It's going to be a hot one though, especially like 104 today, so stay cool, stay hydrated, drink lots of water, and do lots of math. Hey, okay, did anybody feel the earthquake this morning? I did. It was pretty much intense. It was pretty cool. Does anybody else have anything else that they like to share? Any happy news? Anything they want to let everybody know? Anything they're going to do for this weekend? All right, so we'll move on to our warm-up, and then after a warm-up, we're going to review exponential and linear functions, which will segue us into our new unit of exponential and linear growth. And then we'll let you guys do some classwork and practice it, and then from there we'll do an exit ticket. And if you guys have any questions, please let me know. Please feel free to stop me. Let me know if I go too fast. Just say, hey, Mrs. Van Gessel, hold up. You're going a little too fast. Or if you have questions, please stop me. And if you have questions afterwards, feel free to send me a note, and I'll get back to you as soon as I can. All right? Okay, so let's get started with the warm-up. Go to your Google Forms, and you can start accessing the warm-up. Okay, so there we have it. Here's our warm-up. It's going over how to solve for exponents and evaluate the expression for x equals 3 when you're given an exponent. I just wanted to review how when you have a number to a 0 power, what do you get? And if you have a number to a negative exponent, what do you do with it? Okay, let's see if you guys remember how to do those. All right, looks like people have answered. And yes, you guys are accurate. When you have when you have the 4 to the 0 is a 1, so any base to a 0 power is 1. And if you have a negative exponent, that's going to make it to where you do the reciprocal, if you remember that. So you're going to flip it, which is why we get 1/9 for number 3. Okay, now let's do a review of exponential and linear functions. What is an exponential function? Well, it's our equation where y equals ab to the power x. Okay, to exponent x. And it's an exponential function in which the independent variable is an exponent. Okay, where a is our initial value, b is our base number, if you remember, and x is our exponent. Don't forget to do order of operations when you solve for these also. Don't forget to do your exponent first, and then you multiply it to the a. And it's also represented in a curve. Okay, and as you will see the next problem, you'll see that it gets very, very close to 0, but never crosses for the y value. Here's an example where y equals 2 to the x. If we have our values where x equals negative 3, negative 2, negative 1, all the way down to 3, and we solve for it, we take our x value, put it into our y equation, which gives us y equals 2 to the negative 3, and it gives us 1/8. Remember, the negative makes us do the reciprocal. So down here you have y equals 2 to the 3rd, which gives us 8, and 2 to the negative 3rd gives us 1/8. Okay? And here's our graph. And as you can see, we get very close to y being 0, but it's not going to be 0. Not going to go 0. Okay, it gets very, 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 very small as the x value gets extremely small. Our y value gets very, very close to 0. And so here's some key features to remember. When x is less than 0, y values get smaller and smaller and smaller, but y will never be 0. Okay? And as x is greater than 0, the y values grow exponentially. And you have 2 to the first, which is 2. Then you have 2 to the fourth, which would be, or let's do 2 to the and 2 to the 4th is 16, so it's a lot more. When b is greater than 0, it is considered an exponential growth. That is key for later on when we start talking about exponential growth and exponential decay. Okay, and when x is 0, y is equal to 1. What is a linear function? And linear function is a function, it's an equation of a line, it's the shape of a line, where b equals the initial value, y, which is the y-intercept, m equals the slope, or the constant rate of change, and as I said, it's represented as a straight line, which is why we have our y-intercept form, or our equation of a line. Any questions so far? All right, here's an example of a linear function, y equals 2x. Again, we have our values for x, we put them into our equation for x to solve for y. We get our values of y, and here is our line that we get from our equation, from our linear function. As you can see, it's a straight line. All right, now we're going to check for some understanding. Again, use your Google Forms. You can submit your Google Forms so I can put this down for participation. Y equals for the x, where x equals 4. As you'll notice, the first two equations are exponential equations, whereas the bottom two are linear equations. Okay, you can check your answers. Now we're going to talk about exponential versus linear growth. And what is exponential growths and linear growths? What could they be? There's a lot of things you can use it for. It's very much used in science, where the coronavirus data is being, you hear a lot of talk about exponential growth with that, an exponential basically exponential growth and decay for trying to bring down the coronavirus. It can be used for population, many different things, as well as linear growth. And now we're going to watch a video which tells us more about linear and exponential growth.
As high school students and adolescents, you have a lot of experience with growing. You've been tracking your growth for years now. But today's lesson is going to introduce what might be a couple of new words on the subject: linear and exponential growth. Mastering these will help you grow your SAT score. So let's get started. Linear growth means growing at a constant rate. Each step in growth grows exactly as much as the previous level did. For example, if you deposit $10 into a piggy bank every week, your savings grow at a constant rate. At the end of the first week, you have $10. At the end of the second week, you have $20. At the end of the third week, you have $30. Fourth week, $40, and so on. Every week, you're adding $10. If you find yourself adding the same amount to achieve each new step of growth, you're talking about linear growth. Linear growth can be represented with a straight line, like this graph of our piggy bank savings account, and can be represented with a linear function, y equals mx plus b, where y stands for the amount of money in the pig, x is the number of weeks, and m is $10. Since we started with nothing in the bank, b, the y-intercept equals 0. So our equation would be y equals 10x. If we had started out with $5, then our equation would be y equals 10x plus 5. Now that we have a definition for linear growth, let's take a look at exponential growth. Exponential growth means multiplying by the same amount to achieve each new step of growth. Think about rabbits, or more specifically, think about rabbit populations. Let's say we start with 2 rabbits, and every month they produce 2 new rabbits. And then pretty soon, all those rabbits start producing rabbits, and the rabbit population is doubling every month. So we go from 2 rabbits to 4 rabbits to 8 to 16 to 32. Every new step of growth means multiplying by 2. Multiplying by the same amount to achieve each new step of growth, that's exponential growth. Exponential growth is represented with a curved line, like this graph of our local rabbit population, and can be represented with an exponential function like f of x equals b to the x. Remember, f of x gives you the y value of a graph, so we can also write this exponential function as y equals b to the x. In the case of our rabbits, f of x, or y, stands for the number of rabbits. B stands for the base number of rabbits, we started with 2, and x stands for the number of months. In the first month, we'd have 2 to the 1, or 2 rabbits. In the second month, our number of rabbits would grow to 2 squared, or 4. In the third month, our number would grow to 2 cubed, or 8 rabbits. And then 2 to the 4, and 2 to the 5, and so on. The number of rabbits would be growing exponentially. This graph would need to start with x equals 1 because we need 2 rabbits to get the ball rolling. If we had started with 4 rabbits, our equation would have been y equals 4 to the x. So we've learned that linear growth means we're adding the same number to each step of growth, and that exponential growth means we're multiplying. In addition to growth, the SAT can ask you about decreasing, or shrinking or decay, which is basically the same thing, except your population sizes will be shrinking instead of growing, and this shrinking will be reflected in the graphs. A graph of linear decreasing might look like this, and a graph of exponential decay might look like this. Now,
Okay, they're going a little further into exponential decay and exponential growth. We're not quite, or linear decay and linear growth, or exponential growth. We're not quite, sorry, exponential and linear decay is what they're talking about, which we're not quite there yet. That'll be a little bit later. Okay, so again, exponential versus linear growth. Exponential growth is determined by the value of y increasing by a growth factor with the equation y equals ab to the x. And a is the initial value, b is the growth factor, which you can calculate from y2 divided by y1. And then linear growth is determined by a constant rate of growth in y, where you have y equals mx plus b. Okay, where m is your rate of change and your b is your initial value. When the data, now there's times where we do have it where data might not be exponential or linear, and that can happen. And when that does happen, the data that, do you know that based on the fact that the data doesn't have a constant rate of change or a common ratio factor, a common growth factor, and therefore it's going to be neither linear nor exponential. So here, let's look at some data that we've been given, and let's analyze it. So here we have, is it going to be linear, exponential, or neither? Okay, so for the first one, we look at our x values, and do they increase at a constant rate, at a constant number? Yep. They all increase at 1. They'll have a factor of 1 with increase. And now our bottom, we're going to see how the difference is here, if it also increases at a constant rate. So our y values, yep, our y values are increasing. If we do y2 minus y1, we get 6. y3 minus y2, we get 6 again. And so on and so forth. The difference between the values is 6. It increases by 6 to each value. Therefore, it's going to be a linear growth. Okay, x increases by 1 value, y increases each time by 6, as determined by y2 minus y1 or y3 minus y2, and so on and so forth. And therefore, it's linear. And now let's look at the bottom one. It's a little bit different. It starts off at 1, but again, our x values still increase by 1. Okay, but let's look at our y values. Our y values don't quite increase. Maybe it goes, it increases from 1 to 4, that's a difference of 3. Now from 4 to 16, it's a difference of 12. And then we have a difference of 48, so on and so forth. So it's not going to be linear based on that. But now if we look at the ratio where we take our 4 divided by 1, it gives us 4. So maybe there's a growth factor in there. And again, okay, 16 divided by 4 is 4. It's starting to see a bit of a pattern here, you guys. 64 divided by 16 gives us 4. So it's all to the power of, so it's all with a factor of 4. So this is telling us that we're doing, it's an exponential growth. Okay, so it increases, x increases by a value of 1. Y does not increase at a constant rate, therefore it's not linear. but y does increase each time by a factor of 4, and therefore this is exponential. Any questions? Okay, here's one more. Let's do it. One more. I'm going to give you guys a little time to look at it before I go over it. And then I'm going to, okay, no, here let's go. Again, now we have it where we don't quite increase, our x values don't increase by 1. They increase by 2 each time. That's okay. It's still constant for our x values. What about our y values? Our y values, let's see here, down here, increases by 2. This difference here is 4. It's not looking so good. Now it's doing 3, and 10 to 15 is a difference of 5. So I don't think it's not linear based on the fact that it's not increasing by a constant amount. Now let's see if there's a constant ratio or factor. So 3 divided by 1, 7 and 3. I don't quite see a pattern there either. So this is going to be one of what? Yep, you guys got it. It's going to be neither. X increases by 2, but y does not increase by a common ratio factor or at a constant rate. Therefore, it's neither linear or exponential. Here's kind of a graph that I thought was kind of cute. Okay, now here, why don't you guys do, take some time, break off into your Zoom groups, your Zoom breakout groups, and work on these for a few minutes. And we will review them, and you guys talk to them and show me what answers you guys get. Okay, work with your groups and let me know. I'll give you a few minutes. Okay, and so the first one is linear. Good job. What do you guys get for the second one? Exponential. Great job. How about the third one? Yep, that one is neither. Great job. Okay, now we're going to work on word problems because you tend to get you get a lot of exponential growth and decay and linear growth and decay word problems. And this is where you typically see it a lot, especially in science and different applications. Here we have one where it says a library has 8,000 books and is adding 500 more books each year. How many books will a library have after 4 years? And then they want to know if it's a linear or exponential growth, and then write the equation. Well, let's see here. How do we know if it's linear or exponential? Well, linear is if it's going at a constant, or if it's something's added to it at a constant amount. And actually, if you look at this, it has a word right here that says adding. That's going to be a huge key. You're going to know it's going to be linear, and it's adding 500 more books. So that's your M. That's your growth, your constant rate of growth. Okay, and what's your initial value? 800. So here you go. The total library. So it's the total library of books increases by 500 every year. So 500 equals the constant growth rate. Therefore, it is linear. And here, then the equation y equals mx plus b, where m equals growth rate, which is the 500. Initial value, b is initial value of 800, and we get our final answer of 10,000 books. It's quite a few books. That's awesome. Okay, now let's do another one. A bank account. Now this is a good one because for you that want to, for making money, this would be a great one. It's a bank one, and this is where it's used a lot, especially for exponential growth and decay, where you take a lot of money out or you put a lot of money in. A bank account starts with $10. Every month, the amount of money in the account is doubled. How much money will be in the account in 3 months? Is this linear or exponential growth? Write the expression. Well, again, let's see here. So we start off at $10, and what's our key term here? It says it doubles. So it's not adding, it's a factor of 2, right? So since it's doubling, it means it's going to be exponential. So therefore, it's an exponential growth. And the bank doubles every month, so the growth factor of 2. Therefore, it's exponential growth. If we use our equation, put it in where the growth factor is 2, our initial value is 10. Solve for our equation, and we get that after 2 months, after 3 months, you will have $80 in the bank after starting off with 10. Not too shabby. Okay, here you go for this. Here's another equation or another word problem. Please work with your breakout group with solving this one. See how you guys do, and I'll come back to this later. Okay. And we'll continue on further with doing more word problems and then using it with data tables.